I would like to thank the sponsor of this video, Statistics.com, who has been educating students and professionals in data science from all over the world for over 20 years. But more about that later. Let's get started. Hello and namaste. My name is Brandon, and welcome to the next video in my series about time series. In this video, we will learn about the basic visual patterns you might see in time series data. And of course, like, comment, and subscribe. So let's get going. As I'm sure you have heard many times before in statistics, always view the data, in this case time series, and a time series plot as a first step. Always go for some simple visuals first. Why? Well, initial patterns may become evident. Outliers may well be detected. A sudden change in level could be seen. Missing data, both individual points and spans of time, can be identified. And domain knowledge or common sense explanations might become apparent, like we will see in the next slide. So always look at an initial time series plot as a first step. So here is a personal example of a time series plot. So this is the energy usage in my home per day from June of 2021 through August of 2022. On the y-axis, we have kilowatt hours. So a kilowatt hour is exactly that. If we take 10 100-watt light bulbs and run them for 1 hour, that is a kilowatt hour. That's how much energy is used during that time. So usually you can see that on any given day, I'm using around 33 or so kilowatt hours if you were to average that out. But there are some anomalies in this time series graph. The first obvious anomaly is this spike in the middle. First, let's look at the dates. That occurred in January and February of the year. Now, if you know where I live, which is in the Midwest of the United States, that is the deep winter. So we would expect more energy to be used during those winter months when it's very cold. However, it doesn't appear that this follows the normal pattern. We can see that, the energy usage goes up during the winter, but then there's this huge spike where my energy usage almost tripled, or more than tripled during that time period. What's going on there? Now, I know the answer to all these, so you have to stick around to the end to find out the explanations. Now, we also have two dips here in the middle. What are those? Those seem out of the ordinary. We also have some spikes here along the top of the graph. So we go along for a while, we have a spike, and then a spike. I did not circle all of them, but if you follow your eye across the top of the graph, you can see these occasional spikes. I know what those are. So if you think you do, wait to the end of the video and I'll tell you what those spikes are. And then there's one other dip here in the lower left. What is that? That looks like the orange dips in the middle of the graph, but that's actually something else. And I will tell you what that is again at the end. So we do this first visual time series inspection. We look for anomalies, look for things that look out of the ordinary. We look at patterns. We look at seasonality in some cases, and then we go from there. But first, always do a time series plot. So time series has several components that are common. So first we have level. That's the current value. In the previous graph, the level is kilowatt hours. That is the amount of energy I used on any given day. Next we have trend, which is changes in the values over time. So in general, the trend can be linear or a straight line, or it can be nonlinear, so it can curve. Then we have seasonality, which is a repeating, evenly spaced pattern. So it can be additive, which is constant or stable, or it can be multiplicative, non-constant, growing or shrinking. Of course, a common sense example of seasonality is store sales during holidays. You'll see spikes in sales in the fourth quarter for many stores, depending on where you are in the world because of holidays, and then it will go back down or severely go back down in January. And there are many other seasonality things you can think about. Stores, depending on where you are, stores sell more umbrellas in the spring, at least here in the US, because that's when it rains more. So you can just kind of see the idea of seasonality. Now, seasonality can be other things you wouldn't normally think about. So those white circles in the previous slide of my energy usage might be a seasonal pattern, but of course it's not seasonal in terms of the seasons of the weather or anything. And then we have noise, which is random fluctuations in data. So the four time series components to think about are level, trend, seasonality, and noise. Now, all time series have level and some noise, but may or may not have seasonality and or a trend. If you prefer, you can think of all time series having all four components, but some components are essentially zero. Time series components are not yes or no. They are a matter of degree. And visual analysis of time series data is dependent on the time window. So larger time windows tend to smooth out the series if we kind of zoom out. Localized short time windows can exaggerate level changes if we zoom in. Now, this isn't always a hard and fast rule. It really depends on the data. But if you really zoom into a time series and then change the scale on the y-axis on the level, it can exaggerate level changes that in the grand scheme of things really aren't that big. And we'll see an example here in a second. So you must always pay attention to the value scale. Some of them can change as you zoom into them. There are many online tools that offer interactive graphs for time series. However, if you're not careful, when you go in to look at a shorter time window, they, for some reason, will go ahead and change the level scale, and that can exaggerate changes over that period of time. So here is an example. This graph represents the percentage of individuals using the internet in Japan from 2013 to 2020. We can see the scale is from 0 to 100 because that is the possible range in a percentage scale, and it hovers right around 90% for those years. A little bit higher, a little bit lower now and then, but in general, this is what we call a very constant trend. Now, if I change the scale on the level on the y-axis, now look what it looks like. This is the same graph before, but now the scale on the left has been changed from 88% to 94%. And that flat line, that constant looking trend, now looks a lot different. So always, always, always have to pay attention to the level scale that's being used to know whether or not the changes in level are being exaggerated or attenuated. And finally, in this time series plot, we have this data going back to 1990 and then all the way through 2020. So you can see here that obviously in around 1990, there really wasn't home internet or internet at all in homes anywhere. Then of course, as we got into the mid 90s, that tended to increase. And then into the 2000s, it increased steeply. And then we kind of reached this sort of plateau once we reached, 2013, 2014. And for perspective, this is the area we looked at in the previous two slides. We were just zooming in to that point. So it's very important to keep in mind the level scale on the y-axis and of course the time scale along the bottom axis, because it can drastically change the interpretation of your time series plot. So two basic component models. One is additive. In this case, it's level plus trend plus seasonality plus some noise. Then there's multiplicative, which is level times trend times seasonality times noise. And of course there are others, but these are the two basic component models. The main difference is that in an additive change, values change by a constant amount. With multiplicative change, values change by a percentage amount and often take on V-shapes or curves, and we'll see those here in a second. When conducting time series analysis and or making predictions, we are essentially deconstructing the time series back to a constant level. We flatten out the series, removing trend and seasonality. So when building time series models, which are different than a traditional time series prediction, we'll talk about that later, what we are essentially doing is backing out these components. We're going to back out the seasonality. We're going to back out the trend. So really, all we're left with is a constant level and some noise. Now, some time series methods require or assume a constant trend. You have to have time series data where the seasonality is removed and it is detrended before you can actually implement the method.
This is Business Analytics using forecasting.
Hello, and welcome to Persuasion Analytics.
I will be your instructor in the next 4 weeks as you learn about interactive data visualization methods.
This course will be an exciting opportunity to learn about and play with modeling that's influencing our daily lives.
Data and statistics touch every facet of our lives. In fact, that is why you are here on my channel. Statistics.com is committed to preparing the next generation of data analysts, just like you, while being human-centered. And, depending on your school, you might even be able to earn college credit. Classes are relatively small and personal. As a student, you aren't just a number. You can ask questions directly to your instructor, who, quite often, literally wrote the book, and receive a quality education with a personal touch. Statistics.com was the first online education institution approved by the American Council on Education. In the beginning, only one course was offered. Now, 75 courses are offered, covering the gamut of data science education. Many students are working adults from all over the world, and because courses are offered asynchronously, students can still maintain a career, family, and personal interests while also studying what they need to learn to take the next career step as a data science professional. For more information and a special discount offer from Statistics.com, please see the description below. Now, back to the video. So our first visual here is a constant trend that's non-seasonal. So our time series goes along. There are spikes, there are ups and downs, but those ups and downs don't really follow any regular pattern. They're kind of random. And of course, the trend is flat. You can kind of think of this as home base. So many time series methods want to get back to this point by taking out any seasonality, like I said, by taking out any trend, and really sort of getting back to this point, and then we can analyze what we took out to get to this point. That's how it works. Next, we have an upward linear trend that's non-seasonal. So as the name indicates, we have an upward linear trend. It doesn't have any regular seasonal patterns, and it looks something like this. Of course, it could go down, but in this case, it's going up. Then we have a constant trend additive seasonality. So here we have regular spikes and dips along the time series at a regular interval. So what we do in time series is try to figure out what that interval is and what level changes happen at those seasonality points. Next, we have upward linear trend and additive seasonal. So now we're taking the linear trend and adding in the seasonality. So again, it looks like this. And I did not circle all of the seasonality points here, but you can kind of follow the pattern. So these ups and downs might follow a regular pattern, and we have a trend and seasonality. Constant trend multiplicative seasonal. This is where things get a bit different than what we're used to. So here we can see that the time series becomes more variable over time. So the ups and downs follow a V shape over time. So in this general case, it's seasonal, but the distance between the up season and down season gets wider over time. And that's what we mean by multiplicative seasonal. Then we have upward linear trend, multiplicative seasonal. Same thing as the last graph, it's just tilted because it is a linear trend, and you can see all the seasonality points here. Next, upward exponential trend. So now we're getting into curves. So a time series might look like this as an upward exponential trend. This obviously looks a lot like, ideally, what your savings account or investment account would look like if you put money in there and then it compounded interest, right? So you can think of this as kind of like compound interest. So in this case, the level changes a lot like your savings account or investments. It's compounding upon itself, and therefore it takes on an upward curve. And of course, the curve could go down as well. We could also have things like third order polynomials, which kind of look like this. We could also have sine waves. So a pattern could look like this. There are definitely time series components that can be modeled using the sine term in the function. A good example of this is energy usage based on seasons, because usually we'd think that, oh, well, one of the seasons we use more energy and then one we use less, and the other two are kind of in the middle. In this case, it's a bit different, right? Because we tend to use more energy in the winter. If you live somewhere where there is winter, we tend to use less in the spring. We use more again in the summer to cool off, and then less again in the autumn. So here we have this pattern of usage. Up in winter, down in spring, up in summer, down in fall. And it follows this sort of sine wave pattern. So here is another example. This is the Commonwealth Bank of Australia. It's its price going back to 1992. So you can follow along and see that it has an upward trend pretty steadily all the way from 1992 to 2007 or 8. And then what happens? The bottom falls out. Well, why? Well, of course, that was the Great Recession. So you can see that the price went from 60 all the way down to below 30. It lost half of its value from peak to trough. And of course, I put this on here because it's important to always look at this time series in total first, try to come up with some explanations, and then see if you can make sense of it before going in and doing any sort of analysis. You can see here that, yeah, there's an upward trend, but the trend tends to take on different slopes. So we can see that from 92 through 2007, that tends to be a fairly gradual slope over time. It might be even slightly curved. But if we go back to 2008 and then go to 2011, it goes almost straight up. Of course, then it changes again to go down a little bit, and then it goes straight up again almost at a steep angle. So the trend can change in terms of its steepness at different points in time, up or down. Always, always, always look at a time series plot. Another example is the global temperature. This is from NASA. So here we can see the global temperature change in the anomalies from 1880 through 2020. We can definitely see an upward trend here. It's probably slightly curved as well. And we can look through time and see if there's anything here that makes sense. So one thing that stands out to me is this here, this bump right around 1940, early 1940s. Now, why might that be? Well, that was World War II. So one hypothesis here that could be proven or not supported is that World War II, because of all the ordnance that was going off, because of all the manufacturing that was going on, created a temperature anomaly during that time. But of course, that would be something we could go back and look into more. But without looking at our time series plot, we wouldn't even know it's there. And of course, in this case, it helps to know some world history so you can explain exactly what might be going on there. Now, while this is not measuring the exact same thing as the previous slide, this is the same basic idea. So this is a graph of the global average temperature change going back 2,000 years. So what we can see is the graph is pretty steady and flat for the first 1,000 years. Then it seems to decrease for the next 600 years. Then it's pretty flat again. And then all of a sudden, in the mid-1800s, it just goes bananas. Okay, it goes crazy. Now, what we have to do looking at a time series is maybe figure out why that might be. So of course, the way to explain the last 150-year spike here is industrialization. Once we started burning more coal, burning more oil, and putting more gases and other things into the atmosphere, the global average temperature change skyrocketed. And it correlates with what we know about history. So we can see here, over the course of this time series, we have to know some things about the world around us, and that can help us explain what we are looking at. So here are the answers to this riddle about my energy usage. First, the blue box. What's going on here? Two things, actually. One, my furnace was malfunctioning. It was not running optimally, to say the least, and therefore it was running on auxiliary power constantly. That's like the high energy mode of the furnace. On top of that, we had an extreme cold spell during that time. So those two things combined created this huge, massive spike in my daily energy usage. So there were times when I was using over 100 kilowatts of energy per day because my furnace was malfunctioning during a time when it was very, very cold outside. And those combined created that. Now, of course, I figured out what was wrong with my furnace, got it fixed, and you can see that it went right back down to where we'd expect it to. But my energy usage tripled, or more than tripled, during this time. So what about the two orange circles? Well, those were times when I was actually out of town. So I was not in my home at all on those days. You can think of that as kind of like the baseline energy usage of my home when I'm not even here. So the heating and air system was set to a very efficient away mode. I was not here using electronics like TVs and computers and other things like that. Now, other things were still plugged in using energy. So my refrigerator was still plugged in and keeping everything in there cool, but I was not opening and closing the door, multiple times per day, which uses energy. And of course, other things along the way. I wasn't turning on any lights because I wasn't here and stuff like that. So we can think of this as a baseline for energy usage of my home when I'm not even here, which is about 10 kilowatts per day, just to keep everything that has to stay running. Now, I know this because this is my data. This is data about my home. I know where I am and things like that. But if you extrapolate this to data that is not about my home, or you're using data that is not personal to you, you still have to go out and try to come up with or find out answers to these questions along time series data of why certain things might be happening. All right, what's next? What are the white circles? Laundry days. So the little spikes along this time series are days that I do my laundry, which is by far the most energy hungry appliances in my home and in most people's homes. So every now and then, usually about every week or so, you'll see spike. That is the day that I would do my laundry, usually on Sundays, but not always. So I can tell over this time series plot that doing my laundry adds approximately depending on, how many loads I'm doing and stuff like that, can add anywhere from 10 to 15 kilowatts of energy to my budget that day. So I can plan that out. I can do it on off days or off times, knowing how much energy it uses on average. But that explains the little spikes along the way. And then finally, what about the purple circle down there? I told you that that's not a day that I was out of town. So what explains that purple circle? Now, what explains this purple circle in the lower left-hand side? I told you that's not a day when I was out of town. I was very much in town. So what happened? Power outage due to a storm. We had a very severe line of thunderstorms go through our region, and it knocked out power to pretty much everyone. So of course, on a day when you don't have any electricity, you're going to use less. And in this case, I didn't use 0 because the power wasn't out the entire day. It was out most of the day, actually into the evening and night. It was very, very hot. It was miserable because no one had air conditioning. It was hot outside, and it was just an all-around bad experience. But that's what happened there. And only I would know that because, again, I'm living in this house. Sometimes you have to do some sleuthing, some investigations to figure out what's actually going on in time series data, like all data for that matter. And then finally, the rest is a very consistent pattern. So you can see that my energy usage hovers between 20 and 40 kilowatts per day with an average of about 35 or so, somewhere around there, 30 to 35, which is very consistent. So my routines are very similar day to day. The only event that happens in my home that's typically very energy dependent is doing laundry. So aside from the seasonal changes in energy usage due to the weather, the only other energy intensive activity is doing laundry. So it was really interesting for me to get this data and look at it and try to explain all these different parts of it. And then of course, what it allows me to do, it allows me to forecast, because my usage is very consistent, how much energy I'm using per day. More importantly, what it allows me to do is make changes to my energy usage, and then I can see if that change affects the level in this graph. If I do things a bit differently, if I try to be more efficient, usually what will happen is I will see, or hopefully see, this average level change after I make that adjustment. Okay, so that wraps up this video on a visual introduction to time series. I hope you found it very helpful and educational, and I will see you again in the next one. Take care and bye-bye.